everyone. Today I'll be talking about the KL42 Enhanced MIPS processor that I designed for the CUCS 440 Computer Architecture class. So begin with a brief overview. I'll be introducing the name of the processor, a brief description of the specifications, go into the hardware implementation, current enhancements, the future enhancements, and then a brief question and answer session. So to begin with, why the name KL42? Well, first of all, it's an easy name to say. It really just rolls off the tongue. K and L are right next to each other on the alphabet, which is familiar to nearly everyone. And 42 is a very safe number. It's even, and it's the product of 3 primes, 7, 3, and 2. So a brief overview of the processor specifications. The MIPS processor has a 32-bit instruction word format with 4 distinct types, not 3. So we have the R type, the I type, the J type, and a new type called the MD type, which I'll be discussing later. And this processor uses a Harvard memory architecture with separate data and instruction memories. So there are 2 main data types, 32-bit signed and 32-bit unsigned integers, 4 different addressing modes: immediate, register, register indirect, and PC relative. In immediate mode, the value itself is an operand in the instruction mode. In register mode, the registers contain the values to be operated upon. In register indirect, the memory locations are accessed by a value stored in a register plus an offset to access the specific data word. And in the PC relative mode, PC is supplied with an offset or concatenated with values to perform branches and jumps. And it also supports interrupts and is able to use the stack pointer or the return address register to return using the JR or ready instructions. And the reset will cause zeros to be written to $0, stack pointer to be loaded with 3FC, and the flags register to be initialized with all zeros. So now we're going to get into the hardware implementation. Here's an overall block diagram of the CPU, EU, and I/O space and memory module. Here we can see that the memory module and I/O space can receive addresses from the CPU, EU, which also outputs data that the CPU, I/O space, and memory module will use. And then on an output or on an input instruction or a load word, the data out will come from the memory module and the I/O space and return to the CPU, EU. And here's an overall block diagram of the IDP. You can see the T address MUX and the S address MUX, which are used for the stack pointer returns. And over on the ALU, you can see that I've added 2 new ports for my enhancement: the divide location and multiply location, as well as the divide select and the multiply select. The divide location and multiply location are found in the instruction word, the MD instruction word. And then the divide, div cell, and mul cell come from the control unit. And and here is the instruction unit. PC MUX can take PC in from the IDP, branch address, the jump address. Here's the program counter, which can be loaded or incremented. The instruction memory, which has a chip select, read and write, which goes to the instruction register, and which goes either out through the sign extend or to IR out to the rest of the processor, or to the IDP. And this is the memory module, receives data from the IDP, receives an address from the IDP, both the CS, chip select, read, write, and it returns a value to the IDP through that D out. instruction list. So I added a few instructions, some of which use the E key, some which unfortunately do not, but I would look to fixing that in the future. So current enhancements, I added approximately 15 new instructions: multiply byte, multiply half word, divide byte, divide half word, branch greater than or equal to 0, branch greater than or equal to 0 in length, branch less than 0 in length, the DJ and Z instruction, decrement jump not 0, the not and not, exclusive nor, change sign, negate, move, and clear. So in the multiply byte instruction, it allows for the multiplication of individual bytes between two registers. However, the bytes must be from the same position in each register. At current, there is not a way to allow for mixed multiplication of bytes. And here you can see the instruction, which just looks at the mulloc field and multiplies the correct byte.
You want to explain the mulloc to everybody?
Yes, I'll be explaining it in
Okay,
2 slides.
Great.
And multiply half word. This is similar to multiply byte, except for it allows the multiplication of individual half words. And it has the same restriction as the multiply byte, which can only be used on the upper or the lower half word. There's no mixed multiplication yet possible. And here, so multiply byte, multiply half word instruction format. So in this format, the ALU accepts bits 6 or 7 for the instruction word to determine which byte or which half word of the 2 registers it needs to multiply. This format's based upon, I base this format upon the R-type format, except you'll notice that the shift amount field has been replaced with the divide location and multiply location fields, with 1 bit remaining, which it remains unused. The destination register format is also left blank, as the results will be loaded into the high and low registers as in a regular multiply location. And we have the opcode at 1/2, and then the actual function to be performed is located in the function field. Oops, my bad. And divide byte, similar to multiply byte, except it allows for the division of individual bytes, except that unfortunately at current, bytes must be from the same position in each register. Divide half word, similar to the multiply half word, except it allows for division of the individual half words between 2 registers. Just a quick overview of the instruction format for this. In this case, we don't use the multiply location field, but instead use the divide location field, which is included in the instruction word. The shaft was replaced with multiply and divide locations. So here we have branch greater than or equal to 0, which is a single operand instruction. It passes a register through the ALU and then checks the flags on that value. If the resulting value is greater than or equal to 0, the branch will succeed. If not, the branch will fail. And branch greater than or equal to 0 in length in this instruction, similar to branch greater than or equal to 0, except that if this case, if the branch succeeds, then the return address will be saved to the $RA register to be used on a JR, to be used with the JR register to return, or instruction to return. So with branch less than 0, similar to the branch greater than 0, the greater than or equal to 0, it passes a value through the ALU, checks the flags on that value, and if the flags are, if it's negative, then the branch will pass and the branch will succeed, and the PC will be updated with the new value. And if it is not negative, then the branch will fail and it will proceed to the next instruction. branch less than 0 and link. In this case, similar to branch less than 0, except in the return address is saved to $RA, and which can be used to return from the jump or from the branch at using the JR command. And the famous decrement jump not 0. So here, the instruction will decrement a register, save that value back into the register. At this point, I have the RS, and there's the RS and RT fields, which must be the same value. Otherwise, you'd have an infinite loop possible. And then it will, so save the value back to the register and jump to the label indicated if the decremented value is not 0. It's useful in creating loops. We have a not and in this instruction. S and T are knotted and then ANDed together, and then that value is written back into the RD register. It's differentiated from the and not. In the and not, S and T are ANDed together, and then the resulting value is knotted, and then that value is written back into RD.
So that's typically referred to as an AND, correct? This one.
You
You
it's
AND two
similar,
things and then not.
but the resulting value is different.
Say again?
The values of the NAND and the AND are different.
Okay, logically, when we see this, this would be a NAND operation. And then the previous one, you knot both of them and AND them together.
Yes.
And you call that an AND?
The first one is a NAND, a not an AND, and then this one is an AND not.
Okay.
The AND operation is performed before the not operation.
Right. Yeah.
An exclusive NOR where the RRS and the RRT are knotted, and then the result is, and then the two registers are exclusive ORed, and that value is written back into RRD. Next instruction is change sign, which performs 2's complement on RRS and then writes that result in RRD. This instruction uses the R-type format, but RRT is not used. This instruction can be useful in preserving the magnitude of a value while changing its sign. And then there's just a simple negate, which just performs one's complement on RS and writes that into RD. The benefits of this over the current instructions are that without this instruction you would have to, the benefits of this, having this instruction and the change sign instruction, are that if there were only the negate, you would have to do the negate and then an add instruction, which would take more clocks than simply doing a change sign. And then the move, which simply moves the value from RS into RD. And clear, which clears a value, clears a register, fills it with zeros, and then moves that to RD. And some simulation results. You can see that the NAND is in 20, which uses 1 and 2. You see that 1 here, which is actually has been decremented from the TJMZ. So in this case, we have a 688 AA 886 from the NAND, and then the AND N, which uses the same operands as in FDDB, DDF. So they're different operations. You can see the results of the DLT-ZAL, which is the last used, branch and link instruction in register 31. And you can see the results of the multiplies with register 2 and register 1 in 9, 11, and 12. future, I'd like to revisit this processor in order to do pipelining, which I was initially considering for my enhancement, though with time constraints, I felt it better to do other enhancements, adding an interrupt disable, since we already have a set IE instruction, so it would be best to include a way to disable the interrupt, and then multiplying and dividing different bytes and half words. So, are there any questions?
So in essence, those, what did you categorize those instructions as when you could do like 4 multiplies at the same time? That was like a byte multiply.
Could you repeat the question? I'm not sure
What were the, I forget what the mnemonic was for that kind of, where you actually took the 32 bits, broke it up into 4 8-bit multiplies type thing.
Oh, it was, the mult B and the div B.
Okay, that's what it was, yeah.
Right, those instructions use the mul lock and the div lock fields to determine which individual byte that should be multiplied.
So those are SIMD type instructions. I mean,
Oh.
yeah,
Okay,
that's what, single instruction, and you had 4 different data bits that are being multiplied together, bytes.
oh, it's not simultaneous.
Oh, it's not, so it's just 1 byte?
Yes.
Oh, okay. I
Mhm.
thought you changed it so you could,
Mhm.
how hard would have that been?
Not hard.
Not hard, it's really not hard,
Yeah, it would have been easy to do in the future.
yeah. Very good, right? Thank you.